So mutually exclusive means there's nothing overlapping, right? It doesn't happen at the same time in this set and that set. So the intersection, there's no element. Now let's talk about non-mutually exclusive events, which means there is some overlapping part. So both events can happen at the same time. We can explain this better with the set model. If you think back to Math 135, you can remember what set is, and we are so familiar with the Venn diagram, so we're going to explain with the Venn diagram too. So let's consider one spin of the wheel. So the sample space is 0 all the way to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is the sample space. If event E consists of these numbers 0, 2, 4, 6, 8 even numbers, and T consists of 0, 3, 6, 9 multiples of 3, then what is the intersection of E and T? So what is both in event E and event T? So you can see what is overlapping. 0, what else? And 6, right? So 0 and 6 are the elements that are both in set E and set T. So this is the intersection part. If you remember, the U shape upside down of this is called union, and this is called intersection because it's talking about what is overlapping in Venn diagram. Okay, so when you're looking at the Venn diagram, you can see overlapping part here. 0 and 6 is both in event E and it's also in event T, or set E or in set T. How about the other numbers? All other numbers that are not in E or T, they are outside here, right? So we can see there are 1, 2, 3, 4 reasons in this union set U. Well, this is actually sample S, but generally speaking, we call that as universe. But in our specific case, it's better for us to write it as S, but textbook just put the data like that. So I don't like it, but yeah, understand that as sample space. Okay, so what I'm saying here is their union. So event E and event T are not mutually exclusive because there are some elements that are both in both events, right? So we are saying in that case it's non-mutually exclusive, or they are not mutually exclusive. So thinking about the event, probability of event E union T, you can find that probability of that with the same rule. So you're gonna count how many are in E union T, the number of elements in E union T over the total elements of the sample space, right? So what is the union of E and T, number of that? Well, since when you're counting E, we count 6 and 0 there, but when you're counting T, it is counted again. Since this part, the overlapping part, the intersection part is counted twice, you need to take that many out, right? So number of elements in union of E and T should be number of elements in E plus number of elements in T, and you need to take away number of elements in the intersection part because we counted this twice. Once you know that, it's easy, right? So probability of E union T should be coming from this over the total space, total elements in the sample space, everything, right? So just remember, if it's not mutually exclusive, you can think about the union as counting this and that and subtract that are counted twice, that are actually the overlapping to each other. So the intersection part, you need to take it away. Well, you can also apply this to mutually exclusive because there's no intersection. when the two sets are mutually exclusive, this is 0. So taking away 0 is still n of e plus n of t. So it works for, mutually exclusive as well. Okay, so let's summarize probability properties that we learned in chapter 9, section 1. Okay, I will give you some time to consider what goes in this darker green color. Excuse me. So let's go back here. P of empty set. So probability of there's nothing in it in the sample space. So probability of nothing happens should be 0 because it's impossible event, right? How about probability I can go to answer right away. I didn't know that. Probability of sample space. So total sample space, how do you find it? Number of elements in the sample space over number of elements of sample space. So the numerator and denominator is exactly the same, right? In that case, probability of all events all elements that happens is 1, right? So for any event A, we know probability of that event is always greater than or equal to 0 and less than or equal to 1. So the minimum number of any probability is 0. If it doesn't happen, it's 0. There's non-negative probability, right? And if it certainly happens, then the probability of that event is 1, because that's the total sample space, right? So here, 0 all the way to 1, and both are included. So if we say it's impossible, then the probability of that impossible event is 0, and if that event certainly happens without no exception, then the probability of that event should be 1. If, number 4, A and B are mutually exclusive events, probability of A union B should be probability of A plus probability of B, because there's no intersection part. If they are not mutually exclusive, or even including that here, for any events, probability of A union B should be probability of A plus probability of B, and you can subtract the probability of A intersection of NB, right? Okay. If any A is an event, that probability of any A complement of A event should be 1 minus probability of A, because when you add probability of A and the complementary of that is always 1. Okay, so here is the answer. Okay, write this down on your paper. It's very important to understand and remember, because you're going to use this heavily to solve all the probability questions. Okay, so here is one example that we can do. A golf bag contains 2 red tees, 4 blue tees, and 5 white tees. What is the probability of the event R that a tee drawn at random is red? So solve this on your paper. Okay, so we need to start from P of R, probability of R that a tee drawn at random is red is what? You can consider numerator as number of elements in R, which is 2, because there are 2 red tees, right? Over, what is the sample space? How many tees are there altogether in that golf bag? There are 6 and 5, 11. So the probability of the event R should be 2 over 11. I will show you down here too, okay? What is the probability of the event not R? Not R means complement of R, right? So you can subtract probability of R from 1 to get probability of complement of R. So if you already have found 2/11 here, you can take away 2/11 from 1 to get number 2. Part C, what is the probability of the event that a T drawn at random is either red or blue? That is, probability of R union B. How can we find it? You need to consider whether they are mutually exclusive or not. Well, there's nothing overlapping. The T is either red or blue. It cannot be red and blue at the same time. So they are mutually exclusive. So you can just count probability of R and add that by probability of B. Probability of R is 2/11. We already found it in part A. Probability of B, blue T, the probability to get blue T's from here is 4 out of the total 11. So you can add 2/11 by 4/11 and get 6/11. Okay, so I will pause here so you can take a look at the work here and you can understand what I had said earlier. Okay, all right. You can design a geometric model for the following experiment. So tossing a fair coin. Think about it. Coin has either head or tail. So you need to have 1/2 and 1/2 exactly. If you need to design any, spinner for that, you can have 1/2 and 1/2. This is one of, model that I can draw. You can either do, well, there's another way that you can think about. You can make this way into half. It also works, and or you can do making 4 and head tail equally. Then it's 2/4 of each. So 1/2, 1/2, 2/4 is the same as 1/2, right? That's another idea. You can also think about other ideas and add it to that. Just remember, you need to have fair coin or fair die. That means all the regions have to have exactly same amount, same area, right? So for rolling a fair die, you need to have 1/6 of each. So you need to have equally divided 6 parts. This is one example. You can use a circle as well, just like the normal spinner that is always circle. But that's one example with all 6 triangles that are equal. Okay, so we will stop here for this section 9.1, determining probabilities. Hopefully you can solve all the problems in my math lab. Okay, have a good day, guys.